Okay. Welcome to again machine learning for material sciences. Uh, so I think by now, I hope everybody has got some taste of machine learning. We will jump into materials science soon. But by now, you should be able to, if I give you any machine learning algorithm, you should be able to directly tell me, like, I want you to find, let's say, the best W and the best B, or like the bias you can have. You would like come back to tell me and that's okay, gradient descent. Yes, and that answer most likely will be the correct one. We also went through some of the initial introductions of machine learning. Yes, and specifically important, like why choosing the algorithm itself can matter through inductive bias and all. Yes, and just the class before that class we studied one of the algorithms, linear regression. You must have heard linear regression anyway, but that is also a machine learning algorithm that might be new. But given we are optimizing W and B based on the data that we have, training set, that's why it's like machine learning. Yes, because we are trying to build a map between X and Y, like the input and the output through that. Yes, through the data itself. Fine. So with that notion, we will go ahead with the next algorithm. That is called logistic regression. Uh, of course, like logistic regression is, although the name says regression, it is not a regression, it's rather a classification algorithm. Coming back again, just revising regression classification. Regression will give you like continuous set of values as an output, like you can predict continuous values, let's say temperature. Yes, and classification would be more like a limited set of output, like for example, cloudy, sunny, and rainy. Yes, so that would be classification. And why it is called regression? Probably just got too stuck that way, and it looks very similar to linear regression, at least some form of it. So that's why probably name got stuck, and it's called logistic regression. Yeah. And logistic regression, specifically the one that we will discuss, will be more into the binary classification side rather than um, more than two classes side. But that does not mean the logistic regression cannot be used. We'll have some discussions on that towards the end. But for now, whatever we'll be discussing will be logistic regression for binary classification. Yeah. And to state that, of course, like we want like the yi, for example, whatever the output y, to be again a linear function of, let's say, xi. Yes, so our xi is the input vector, yi is the output label. Yes, uh, and we want to still map, but in a linear fashion. But the problem is the moment we have yi is equal to wx plus b, the way we had for linear regression. Uh, our entire yi spread, or like its domain, will range from minus infinity to plus infinity, right? But if we are doing binary classification, it can only have two values at max, right? It could be 0 1 minus 1 1. Yeah. For logistic regression, it is essential that you should have it between 0 and 1. um, Now, like, of course, like, one of the reasons logistic regression was very popular, because like it resembled a linear classification model, so people could do like manual, on by hand they could do this calculations, and they could figure out like what should be the value of w and b. Yes, and if we define like a negative level as 0 and let's say positive level as 1, then our goal is to find some function that will be in between 0 and 1. Yes, it should not be minus infinity to plus infinity, rather 0 and 1. And that function will be basically where, now you understand what we did. So we had wx plus b is equal to yi. But if we keep that open, yi will be from minus infinity to plus infinity. What we want is to remain between 0 and 1, because 0 is one class and 1 is another one. Yes. And then we can take something if lies in something in between, but the maximum values and the minimum values should be 0 and 1. Yeah. And the way, other than if it is not 0 and not 1, if the output becomes closer to 0, we can assign it 0, and if the output becomes closer to 1, we assign it 1. Yes. uh, so what kind of a function has that property? So one is this like standard logistic function or sigmoid function, yes, that is given by f of x is equal to 1 over 1 plus e to the power minus x, let's say. The one function that you are seeing here, logistic function, it is just that the x we have replaced with wx plus b, yes, and we have a function that is parameterized by w and b, fine, and which is equivalent to 1 over 1 plus e to the power minus wx plus b, yes. So that's the, from the logic function is 1 over 1 plus e to the power minus x, and this is the logistic function that we use, yes, which is parameterized by w and b, yeah. And of course, you use the natural logarithm, and the graph looks like this. It's like the maximum value, the minimum value is 0, maximum value is 1, and there is a nice continuous curve, yes. And remember, we require this continuous curves because we are eventually going to, let's say, do gradient descent and find those answer, and gradient descent depends on finding gradient, or differentiability is important, and continuous function, that's why it's very important. And if now the point is, let's say we have this particular function, uh, we understand the output will be from 0 and 1, and we, because output is between 0 and 1, we could take it as a probability also, and we could have a decision rule also, yes. So not just the function, because we're doing classification, we need to have a decision rule. For example, here we could tell that anything if f of x is greater than 0.5, we'll mark it as 1, and for anything else we'll mark it as 0, yes. 0 and 1 are the two classes that we're looking at, yes. And how do we reach to that? So of course, like, we could use gradient descent to find the solution, yeah. Now there are other, now to find this w and b, of course we could go ahead and use the same mean squared error, the way you use linear regression. But instead of mean square error, there is something better that we can use it here, that uses some principle of this probability, right? Because the output is between 0 and 1, could some use. And one of those such ways to do so is likelihood function, yes. And so in loss segregation, instead of squared loss, what we do is we try to minimize the empirical risk. That is, we want to maximize the likelihood function, yes. Uh, and in statistics, the likelihood function defines how likely this observation is according to our model. Yes, we have particular set of observations. Observations is basically x comma y pair. How likely is it? Like, given the model we have chosen this parameter, how likely our existence of this xy pair is, yes. Now let's say we have x and y pair, we can assume that we have some specific values, let's say, and if we apply the model to this, we will get some value between 0 and 1, right? If we apply the likelihood function, we'll get the some value between 0 and 1, yes. And I will go in bit. So, and the optimization criteria here is we can use the like maximum likelihood, of course. Uh, uh, but otherwise, but this one looks, if you look at the top function, the likelihood function, this looks like a product of f of wb xi and y to the power yi, and 1 minus f of xi to the power 1 minus y. It might look a little bit like scary to be the word, but it's like very simple way of saying that if you can imagine, if y of I is, let's say, 1, let's say, assume that the label is 1, then if you see the right hand value becomes 1 minus 1, that becomes 0. So 1 minus fwb to the power 0. Doesn't matter what the fwb is, that entire value becomes something to the power 0. So it becomes 1. So that basically, that part doesn't matter at all. So the only thing that we are left with is fwb xi and to the power yi, and yi is 1. So the likelihood of that becomes just fwb xi if yi is 1. And if the other way around, if yi is 0, then if you see the left hand side fwb xi yi, that becomes 1, and only we are left with the right hand side, right? So 1 minus fwb. So that's all we have, right? It looks maybe a little bit too many things, but it's very simple. Now, of course, we have like a product. The pi capital is a product multiplication, and using this objective function or this loss function or this empirical risk, we want to, let's say, maximize this one because we want to maximize the likelihood of pairs that we observe in our observation like xi comma yi based on the parameters we choose. So as much as this is high, much better. Yeah. So, but there are multiplications and otherwise round, so which is a little bit difficult. So what we do is we do something called a log likelihood. Yes. Which is a little bit easier because the product becomes summation, and then as you can see, it's just summation and then just multiply. Y is multiplied rather than to the power. So exponential is gone, multiplication is gone. Yes, log is entering, but that's also easy to calculate. Yeah? Not an issue. So now, and logarithm is of course like a strictly increasing function. Some of the properties are super essential later. And if you look at this, this is so finding maximum log likelihood is same as doing maximum likelihood function. It's the same thing. And of course, this is a numerical optimization problem, and we could use gradient descent to solve this. Yes. Excellent. And this is a gradient descent if you use. So if you have this loss function that is on an, we are just following from this one. Uh, Instead of maximizing log likelihood, we could do minimization of negative of log likelihood, right? So because maximization has other issues, probably not part of this one, any convex optimization chapter. But what you can do is again negative, we can find the minimum value of this function. So we can take a negative log likelihood. So instead of maximizing log likelihood, we could minimize the negative of log likelihood. That's what it has been done. So the final loss function becomes this. We want to minimize the negative log likelihood. Yes. So that is a function, and then what we do is a similar in the linear regression case. If you remember, we took partial derivatives with respect to the weight, we took partial derivative with respect to the bias, we found out what those partial derivatives are, then we update the weights. Yes, so we take one observation sample, we find what is the gradient, then we subtract the gradient. Yes, I hope you remember subtracting the gradient because it allows us to flow to the point of minimum. Yes. And of course, there is an alpha parameter there, which gets multiplied because it's a learning rate. And we also discussed what happens if we choose very high alpha, low alpha. So something in the middle works out the best. Yes. And if you look at this particular function, just the gradient, the d, the like the partial derivative with wj and bias, if you see, that looks exactly similar as linear regression. Yes, the only difference here will be like it is not like an MA. First of all, it is not wx plus b, rather it is in as a logistic function. Yes, so that's the difference. Now, like that is the logistic function. I'll show you one of the few codes and to see something. Here, what happens if you see this is the function that tries to map. So, given a particular x, it has 1 and zeros, two labels. It tries to find out the best logistic function that can fit here. That means maximum number of values should have the value 1 if they are closer, and maximum number of values which actually have 0 should have the value 0, should lie on the left hand side of the function, should lie on the right hand side of the function. Yes, that's what. And this is like in a like a single dimensional picture, and you can assume that for like a multiple dimension function, this curve becomes, instead of a line, this becomes like a more of a like a multidimensional function. And we choose this decision rule, right? The predicate class is equal to 1. The decision rule comes as a like a point here in this particular function. But if we had like a multidimensional thing, that will be like a hyperplane that cuts through the logistic function that depends on so many dimensions. Yes. I hope you are able to visualize that. And because our decision boundary is an hyperplane eventually, uh, so our initially the class, if you see, they are linearly separable. Linearly separable for here, for example, let's say you assume x246 is whenever x is equal to 2, 4, 6 are there, our values are becoming closer to 1. And whenever it's -2 and -4, -6, the values are becoming, let's say, -1. So we just simply have a linearly separable. That means if one on one side there will be 1 and the other side there will be like a 0. Yes. So that's the assumption here also, that the classes that are there, they should be linearly separable. That means there should be one hyperplane or one point or one line that separates both the classes. Yes. And so there are some inductive biases like email spam is because you could definitely tell if there are more free on money. So there might be those kind of cases which we can immediately separate between spam and non-spam. We could also but the problem comes when we need to have, let's say, non-linear boundaries. We'll come to that slowly. I will show you more examples where this comes into it. There, of course, logistic regression will not work. Yes. So just to repeat, logistic regression again. So ignore the name regression for now. It's a classification, majorly like a binary classification because of the logit function, and it's useful in because it's a we don't sorry uh, the loss function here is basically maximum likelihood, but that includes the product and exponential. So what we do is we take a log of that, so that becomes a log likelihood. But log likelihood also has like a max of it, so we take the minimum of negative log likelihood. Okay, that's what we optimize. Gradient descent is used. You can calculate the derivatives, like the gradients, and then you subtract from the again you update the weights and biases, and you will finally find the W and B that you're looking for. Yes. Excellent. Now I will just show you some of the hints of the implementation. Okay, I'm assuming this is visible. Yes. I'll increase the font. Yes. Okay. For logistic regression also, we will be using scikit-learn. Yes, it's this that will be the library for at least the first half of the course. Yes, and remember we had this import numpy as np also. You can have that matplotlib, that is for the graphing. Numpy is for the vector operations. Sklearn.datasets and make classification. I hope you remember in regression, I hope some of you have tried the notebook as well. In we had this function called make regression, and here we can have make classification, right? So they are specific function to design data sets accordingly. Classification will design classification based data sets. Okay? And then we have the train test split, that we want some portions of the data that is generated for training, some portion for testing. Yeah. And there is a model called logistic regression. Yeah. And if you want to do it from scratch, there's a code, of course, but I'll just go through. So first, of course, we can define the sigmoid function, which is like 1 over 1 by 1 plus, yes, e to the power something. The program equivalent is this. Yeah. The next is fit. Remember the fit function, whenever we have, the moment we applied fit function, it has to iterate, right, through batches or epochs. Yes, and it has to iterate, and then it has to find us the actual, let's say, the optimal weights and optimal bias. Yes. So here also we start with, let's say, all the zeros. We start with weight as zeros and bias as zero. That's a random thing that we picked up. And I hope you remember last class, like in gradient descent, it matters a lot on the starting point of the weights and bias, right? Here we're picking 0 and 1 because there will be like unique solution here, not lot. It's not like a non-convex. And so here the second step is basically cross entropy losses here. The cross entropy loss will be looking similar to that. Now, and we update based on the gradient that we have. So we compute the gradient, and then we subtract the gradient from the original weight and original bias, right? And we can also compute the loss based on that. And once we do that, that's basically we wrote a class for logistic regression from scratch. Or the other way, you can also use sklearn's logistic regression, right? So just find out if I used. Okay, fine. So I think I have not added it here, but okay. So let's say logistic model is here. So the same, remember the similar linear regression from scratch. We are calling the class function, class itself. We are trying to create an object. Object is here is a model itself, and to the model, the fit, we give whatever the training set is, the X pair of the and the Y pair of the training set. Once it reaches, we predict the class. Then we also try to find out the probabilities of that, and then we find out the accuracy. Yes, so remember we had something called an R2 score, and here we have something on accuracy. I think everybody knows, like, total number of good predictions by total number of that exists, that is accuracy, how many we are correct overall. So that's accuracy, and generally in classification, accuracy is used. We will learn about more metrics in sometime later class, but accuracy is one of the metrics that is used for classification. R2 score is something that we use to compare models between each other for regression tasks. Yes. And these are the few diagrams that I have plotted just to see how it happens. So if you look at the left hand side, you see like a lot of blue bubbles and red bubbles. So blue bubbles belong to one class, let's say class 1, and class 0 is the red bubbles. Yes. And oh, this is the prediction. If you see, this is like all the blue classes. So this was left hand side is the actual, middle one is the what we predicted. Yeah? And if you see the predictions, everything on the top is probably blue, and everything is on the red is like everything on the bottom is red. And if you see, like, there is no red available on the top, right? So here, if you can see, there is one red here because this was a true class, but in the prediction we don't have that opportunity, because I told you, like, it's a more of a, like a linear line separator, right? So there is the line, the decision boundary would somewhere be along this line. Yes. So because of that, all the top, everything that is on the top becomes, let's say, 1, and then everything below. And if you see on the right hand side, this basically tells you what were the predictive probabilities, right, of those particular classes. So that means we try to draw sigmoid function, yes, based on the x values, and we predicted the probability. Probability is the f of wb is the probability for us. So if you see, the closer we get towards the decision boundary, the probability looks closer to the 0.5 level, where model is super uncertain, but that's the decision boundary we have chosen. So everything that is up becomes that is, anything closer to 1 becomes 1. So we assign everything as actual 1, even if the probability is lie between 0.5 to 1, and anything below is marked as 0. Yes. I hope this makes sense for logistic regression. Okay. Okay. We are back to the slides. Uh, Fine. Yeah. Okay. Logistic regression, we just saw some implementation. Again, the notebook will be shared. Please go through them. Yeah. Now the next. The next big algorithm is decision tree. So, okay, so we covered linear regression, we covered logistic regression, which is classification, and then we have decision tree. Yeah. Before we jump to decision tree, one question I think I initially marked is, we had something called like binary classification. Anybody has any idea, if I had more than two classes, how can I use logistic regression for it? You can type in on the chat, maybe. So if you understand the logistic regression, we had like 1 and 0. So we can maximum do binary classification. Now, how do we do more than, if we had more than two classes? If we had red, blue, and green, let's say, how do we use logistic regression for that? Any Varun says, can we apply two times? Yes, absolutely. Yes, that is one way to think about it. I think Varun is on the right track. So, of course, so what you can do is you can apply this two times. And what you will do is, let's say I have R, G, B, and B class. So what I can do is either it's R or not R. Fine. So I can find a classification or a model which classifies between R and not R. Yes, not R includes everything that is not R, of course, like blue and green. Yes, and similarly, I can write one more model which basically classifies between blue and not blue. I can write one more model basically that classifies from green and not green. Then if I look at those three models, one is, let's say, LR, LG, and LB. So RGB, I have LR, LG, and LB. They predict basically each color, red, green, and blue, let's say. Now I have three models. Now how do I predict which one to pick? Whichever model gives me the highest probability. Okay. So if LR gives me 0.9 and the others are confused, so I'll just pick it in the red bucket. Okay. That's one way to use logistic regression for multiple classes. Yes. Fine. The next one is decision tree. Fine. And it's a very intuitive algorithm, of course. It's a very super, it has been written the classical model of learning, the classical and the natural model of learning, very close to the fundamental computer science notion of divide and conquer. Yeah. And it's also how we think in general. We generally, whatever decisions we make in our life generally resembles a decision tree, right? Um, the only important thing is basically once we have a decision tree, let's say, we will come to how it looks like. But the goal is what questions should be there in our decision tree. Yes, we'll come to that. And one of the examples here is like, let's say the goal is to predict if you remember the first class course. So the goal is to predict whether some unknown user will like some unknown course. Okay? And we can only answer, let's say, yes or no. Like there is a person A, will it like a course D or not? So then we can only say yes or no. And they can interact with us and we can just say yes or no as an answer. So let's say the first question he asks is the course under consideration systems level. Yes. Those who don't know computer science per se, systems is basically anything that architecture, let's say networking, anything that has to do with systems. So is this course under consideration of systems? Then we say yes, fine. Has the student taken any other system courses? We'll say yes. Has the student liked most of the previous system courses? We say no. Then I will say sure. So that means the course is on the system. The student has taken previous system course, but he has not liked the others, like the system courses before. So I can say with some confidence that, okay, I predict the student will also not like this new course that it has. Hmm. Now, so what is the goal here? So remember what we did. So in the decision making process, we basically asked questions and gave answers to it, right? So now the entire goal of decision tree, or like the algorithm part of decision tree, is this. So what are the questions we should ask? Fine. In what order should we ask? And what answer to predict when we have enough answer? Fine. So here, if you see, if we alter the, has the student liked most of the previous system courses, right? We can just shift the question, right? Is this course under consideration in systems, right? But then we are only asking, has the student liked most of the previous systems courses, only because we've asked the first question that if the current course that you're asking me about is under system, right? So similarly, can we change the order? Which question to ask? And once we have asked a lot of questions, what answer can we give you? Yes. So these three things, if we figure out, then we can also design a nice decision tree algorithm. And majorly the different ways and different tries of decision tree algorithm, like decision tree is a bigger umbrella of algorithms. There are multiple sub algorithms there. We'll study one of them in detail. But all other algorithms try to figure out these three questions. Yes. What questions, which order, and what answer to give when we have reached to a particular point. And if you see, our decision tree looks like this. For example, the first question we asked, is it systems? No or yes. If it is no, then might like, yes, of course. And if it is yes, then of course, has he taken other courses? Yes or no again. We ask if it is like a has taken a course in the morning or like liked other system courses, yes or no, and based on that, yes. So now what we have is we have there are a few components we just saw like the we ask questions that are represented by let's say square rectangles, and then we have final ovals. Ovals are basically what are the decisions, and the edges if you see those are like yes or no, that if it is yes this is the path to be followed, yes, based on the answers. What are the answer to the questions based on an answer that is connected to some other rectangle or some other oval, yes. And what is the goal here? We, of course, we start from the top, the first question to be asked, and then we start going down till we reach an oval. Once we reach an oval, we have an answer. Yeah. And all the algorithms in the decision tree that we have try to find out this, right? This particular tree structure. And yeah, so here we do a little bit more. Not a deep dive, but a reintroduction of what are features, what are labels, what are examples. So here features are basically the questions we ask. Yes, generally, is this a system course? If you look at your general data set that you will have like a table of rows and columns, right? Rows will be every observation. Columns are basically what we call as features. Here the features question we can ask. So for example, let's say we can have a particular student and he can take this particular course, let's say, but that course is basically a column in the table, but that can become a question. Like we can ask a question if this is a system course or this is not a system course, right? The values of that particular feature, like the name of the column is the feature, the value in the column is the feature values, yes. What the output that we're expecting, like absolutely yes or no on he liking or not liking, that will be the label. And one example is one row, that means one data point with feature values plus the label. And training data set again is a combination of all the examples with the known labels, yes. Here we are looking at only supervised algorithms. That means labels are mandatory here. Yeah. And of course, one example I think there's given. So if you see course type, difficulty, previous experience, what was the grade, and overall label. Yes. So that means if you see course type is the feature, the system is the feature value. Yes. And label will be the corresponding label for that. And each row is an observation. Right. Now, what do we do, right? So, given we have so many features, sorry, given we have, let's say, course type, difficulty, previous experience, grade, let's say, we can have so many decision trees, right? So, we can ask infinitely, not infinitely, but large number of questions. Yes, we can ask what is the course type, what is the difficulty, what is the previous experience, what is the grade, right? These are four questions, and based on that, your starting point can be anything, and we can do lots of permutation combinations, which question to ask in which order to design those trees. Now, that's like we cannot do like so many trees and then find out which one of those trees are giving us correct answer. Then what do we do? That means we have to just repeating back. So we have this particular shaded area as our input data that contains all the features and the label. The goal is to design a decision tree like this, which will have rectangles, edges, and ovals. Ovals are what we are most interested in, and the order of rectangles, of course. So what do we do? So we have to design one decision tree like that. So most of the easier way is to do a greedy approach. So the goal is if I could ask only a single question, what would be the most useful question that I can ask? Yes. That means I want to, here the question refers to the feature, if you see. So that means we are asking what is the most useful feature in the data set, right? So for example, let's say we all want to, let's say, go out and eat outside, right? For the most useful feature for us may be like money, right? If we don't have money, it doesn't matter what the weather is, if you have a bike to travel or not, is the restaurant open or not. If the money is not there, we are not going. It's a very simple answer, right? That means having money, it's a very wonderful feature. That particular feature value becomes the most useful feature. Based on that, we could immediately decide what to do and what not to do. Yes. And the moment we ask the question, if you see, the data set then gets divided, right? So based on the answer of yes or no, the data set will, if I have money, no, if I have money, yes, right? If you see, the examples get divided. So if I say, was the course difficult? We'll say hard or easy. All the hard courses will lie on one side, all the easy courses will lie on the other side. What it says, that means every question we ask, or every feature, based on every feature, based on the value it has, the data set gets partitioned, right? That means the observations that we have, all the rows that we have, they are partitioned based on the question that has been asked. Yeah. What do? We keep on doing the same thing. We ask a question, data set gets partitioned. We ask another question, data set gets partitioned, and so on and so forth. And we continue to apply till, if you remember, the data written here, data is pure. Data is pure meaning, if you reach to a particular point, let's say in this particular thing, let's say liked other system courses, and yes, that means all the observations, like if you see each systems yes or no, some of the rows will be on the left hand side, some of the rows will be on the right hand side. And if we go towards the last oval of, let's say, like here, there will be some observations there. Pure meaning all the observations have the same label as like. Yeah. Impure means there are some observations that will be, let's say, not liking, and then like, that becomes an impure. Yes. Or we can stop when there are no more features remaining. That means we have asked all the possible questions we can ask, and that's the most amount of information we can get right now. Yes. And then we need to stop and give a solution back. Yes. uh, Now what do? So we have asking the question, we have to find out what is the most useful one, then we partition, then we do the same thing again and again. We stop only when the partition data becomes pure, that means they have the same labels, or there are no more questions to ask, right? Number 2, number 3, number 4 mostly looks very simple. Number 1 is the most difficult task. That means how do we decide which question to ask? Yes. Now, what do? So, to find out, what we can do is we can ask, like, we can do the histogram of each feature value. Yes. I forgot to put the picture here, but we can see, for example, let's say, that's what I told. Like, for example, if you want to go outside and eat, money is the deciding factor. If that is the most deciding factor, that means we understand that whenever money is no, we are 100% sure that we are not going to eat outside. That gives us a lot more confidence in asking the question of money. Yes, that means the feature of money has to be asked. That is the best question to ask right now. Yeah, because once I know it's no, definitely I am sure that we will not go. That decision is super correct. Yes has some uncertainty, but at least no, we are pure sure. Yes, that's one way to reach there. Yeah? And this one, I forgot to add the figure, so this one will not look clear, but this is one of the basic algorithms that is there, and this does exactly the same thing that we discussed in the previous this guy, like 1 2 3 4, but it's just in more algorithmic format. So here basically it says our main decision tree algorithm is algorithm 2. Okay. Here basically says that if the tree is form of a leaf, then just case. That means if we don't just have a decision tree, we just have one oval point. Doesn't matter what questions you ask, this is the answer. Okay. That means for all the observations that we have, there is only one label. Doesn't matter which course you have taken, you hate it, or doesn't matter which course you have taken, you like it. So there is no point in asking questions, right? That's the most easier answer is to give that the oval is whatever. That means if I tell you a course, you will like it, or if I tell you a course, you will just dislike it. Doesn't matter. Okay? So that's the easier part. Or otherwise, if there is a tree that is existing, then you have to do based on the questions that are asked. You go either left, you go either right. Okay? And there's a recursion principle. Yes. Uh, Now on the left hand side is the how we train. Uh, So here we will do this training exercise. Give me a minute here. So what we do, I will go through the algorithm a little bit. I'll come back to this so that we can have a repeat. Give me a minute. Yeah. Now, why decision trees work? Why they are like really nice algorithms? First of all, this is how we do reasoning most often. And if you give me an answer of yes or no, I can definitely tell you this is why I have given you answer of yes or no. Yes. It's very easy, right? I have told you that you will not like this course because previously you had taken system course and this is a system course and you did not like previous system courses. That's why you will not like this course as well. Yes. And of course, like we take no assumptions as such. Uh, and if the algorithm is really nice, it will find important questions, right? The problem here is greedy strategy, right? So that means we are trying to find out the question that will give us the most good answer immediately. We are not looking at, let's say, global scale. Okay. Like for example, the money question. Maybe money could have been the third question, not the first question. Just because whenever the money is no, it is 100% sure that we are not going. I was most biased towards it in the greedy step. Okay, okay. If I get no, there is no point in discussion. Let me ask that question. But eventually, if you end up like sometimes we have money, but there are too many decisions to take, that means the number of questions we ask becomes too long. Right? And overfitting, I'll come back to that. So, but remove overfitting for now. Just look at the right hand side. If you look at this one can memorize the entire training data, right? If you see, we are building decision tree based on the dataset itself. That means we are not like optimizing parameters that are approximately good as the same W and B. But here we ask the questions on all the rows, then the rows get partitioned to left and right. Again, we ask the questions on the partitioned rows. Again, we go left and right. And we keep doing it till let's say something gets pure. That means eventually, if we ask a lot of questions, we will reach to one particular example that was there in the row, in the like observation set or training set. So eventually, whatever answers I am giving is based on whatever the data that was there in the training set. That means whatever answers I am giving you are based on the memory of the previous examples. Yes. So it becomes more of memorization if we go through the entire decision tree. Yes. The next step is instability. So, for example, here what happens is this one you will understand more as you go, but choosing the best particular block, let's say the first block that we chose it because it was the most confident giving answer, right? The best question we could ask. Now, tomorrow, there, for example, let's say the money is here, and based on the money type, if the money is not there, we are not going. Let's say 100 out of 100 times, 51 times if the money is not there, we are not going. The rest of the 49 times money was there, we took some other decisions. But now similarly, if my friend is also not going, I also don't go. So let's say that was, let's say 52 times, let's say like 50 times just. So it is 50 times the friend was there, I did not, if he was not there, I did not go. If he was there, I went. I went or there were some other questions to be asked. If you look at this is 51 and 50, they're very close to each other, right? What if one more example comes, right? In the earlier case, I chose money because most of the times, whenever the 51 times it gave me no, I chose no. But what if the next time one more, instead of 100 observations, 101th observation came? That particular observation told me that my friend wala question is better. Now that creates an instability in the entire decision. Now the question number one is flipping to question number two, maybe can go to question number three. Question number two can go to question number one, just with a change of one particular row or addition or updation, right? So because of this thing, it is decision tree can be very unstable. Yes, unstable as in the order of the questions that we ask can be very different. It can change, and that's the model. One of the algorithms that is used for building or asking, if you see, again, just going back, splitting, recursion, and stopping, these are very general thing. Only the first thing is what? If I could ask you only one question, what would be the most useful? To answer that, there are many algorithms as such. One of them that uses is something called Gini impurity. I think probably it's called in CART, but we'll check. So what happens here is the same principle we apply. We look at the observation, we find out the most useful feature, then we split. Then for the splitted rows, we ask the same question, and then we keep on doing that till we get all the observations that are pure. That means they have the same level, or there are no more questions to ask. Yes, that is one way to stop. And so here the only thing is what questions to ask, because questions will split automatically based on observation. But what question to ask, that's what Gini impurity gives us. Yes. Now here what we do is, if you look at this, it just tells you that for each feature and threshold, we calculate Gini impurity. Threshold I will come a little bit later, but for let's say feature, for example, let's say here if we have difficulty hard or easy, right? So now for each feature I can either have hard or easy, and based on that I can calculate this Gini impurity. It just says what is the probability belonging to particular class. So here I will try what is the probability of a particular, for example, difficulty to be in hard, difficulty to be in easy. That is equivalent to number of rows with having feature as hard in like feature value as hard on the difficulty column, and number of rows having easy by the total number of rows will be the difficult column. So we calculate individual probability. So we calculate, for example, for the feature of for the feature of difficulty, sorry, for the feature of difficulty, we calculate the pi. Instead of pi, we'll calculate p hard or p easy, and then we do a summation of that, right? So pi, maybe there are 2 rows that are hard, there are 5 rows that are easy, so we do a 2 by 7 for hard, that is pi, and p easy would be 5 by 7. Do a square and then add them up. Once we add them up, we subtract like them from 1. That is our Gini value for it. Yes. Now what can you say, like what will be the best value of this Gini? Yes. So the best value of Gini, basically Gini calculates impurity, let's say. So here we want to find which can give all, like if we do the partition, eventually everything here would be like everything here would be of the same label, right? If every course was hard, then that's really nice, right? Then pi square would be exactly 1, then 1 minus 1, it could be like 0. Yes. The best pure value of like the Gini will be like 0, 1 minus 1. Yes. The rest of the world is don't matter because it's a summation. The worst value could be like if the asking the question divides exactly by half. That means half are hard, half are easy. We are left with the maximum uncertainty, that we are absolutely not sure which way to go, because half of the observations tell us to go yes, half of the observations tell us to go no. Yes. So that means that will be like half square plus half square, 1 by 4 plus 1 by 4, that becomes half, and 1 minus half becomes 0.5. Yes. So the most impure will be, let's say, 0.5, and the purely pure will be like, let's say, 0. Yeah, that's the value of Gini. Now once we have Gini done, okay, this is what we do the weighted Gini after the split. Yes. So remember we calculated Gini this way. We ask the question then splits once we ask the question splits into left and right. Some of the observations, some of the rows split into the left side, some of the split into right side. Now based on that, we calculate something called a weighted Gini. Here we calculate Gini of S left. S left as in whatever is on the left hand side, whatever is on the right hand side. Then we multiply that with their corresponding weight. Weight basically says how many rows were splitted on the left hand side, how many rows were splitted on the right hand side. They are basically normalized over total number of rows. Yes. Once we calculate this Gini split, what we do is we find out uh, this Gini split across. We can calculate Gini again, but we can calculate this Gini split across all the features, and whichever gives us the maximum gain, that is the one we pick, right? So if the splitting gives you like two very pure sides, then that becomes very higher weighted Gini. Yes, that basically says that if you split with this particular feature, then we get very pure partition, or if we split with this that gets very impure, then that's a split we go ahead. Now, why we pick this particular Gini impurity? Of course, there are no such complicated question. This is like a very simple calculation: one minus summation of pi square, which is very simple. This is also weighted. This is just calculates the number of observations by total number of observations. Yes, uh, and we calculate the node purity. Node purity, I said, like 0 is pure node when everything belongs to the same label, and of course, like then what is the stopping criteria that we can use? One of the area is when all the nodes in the label are same. That is, I told, like we reach to a point where everything is pure. Or the next is, for example, it doesn't matter how much we split, there is no gain in Gini. That means Gini impurity remains the same. Yes, and or otherwise there are no more questions to be asked, or we can stop. For example, let's say we reach to a point where we have splitted, but each particular split has, let's say, two observations or three observations, and we rather not take decisions on just two observation or three observation, right? We could stop at a point where we reach minimum number of samples. That means we at least need some confidence, right? At least, like, say 10 examples should be there we can ask and take. And let's say, for example, in 10 examples, at the last oval, there are at least six people saying that this is a course that I will like, and four people are saying not like. That's a better bet than taking like just three samples, right? Two people are saying like and one people. So minimum samples could be a stopping criteria as well. So just to like complete, so we have nodes that are features, and we ask questions. Leaves are where we do the predictions. What is the splitting criteria? One of them is Gini impurity. There is also information gain. You can also do mean squared error that we can do for regression. Yes. Uh, just one moment. I told you that we will reach here. Yes. Now, if it is difficulty is hard or easy, it is very easy to split, right? The question we can ask is the course difficult, then we split into hard, split into easy. That means the feature itself was a categorical feature. That means the output is limited to certain values. What if this was a temperature, right? So let's say temperature, something is 38.2, 36.7, 31.2, 42.3. Now, if in this values, we cannot just split based on the categories. At this particular junction, we have to ask, uh, where is that? Threshold, right? So here what we tell, like instead of saying difficulty, if the question is, if the course is difficult or hard, we say if the temperature is greater than 35 or less than 35. Yeah. So, but then you can understand like why choose greater than 35, why not choose greater than 36? I'm like, I'm with you there. These are all possible combinations. The idea says hopefully with some domain knowledge we should be able to figure it out. That means if I'm asking a question, if there will be this time we'll get good mangoes or not, I can say the average temperature should be greater than 36. I can have that as a, because of my domain knowledge, that it requires a hot climate. But otherwise, if we do not know everything at all, then we have to try with all possible thresholds, which is a very bad exercise. But if we have domain knowledge, we could use that. And of course, like advantage is, of course, it's highly interpretable. I've told already. I think most of the things I've already talked. I will just move to the implementation. Give me like one moment. Implementation, I will be quick. Most of the things I think slowly you are learning anyway. Yeah, I hope this is visible. The major things that I wanted to show is I'll come back to. So these are already there. I just wanted to show how it will look like. I hope you can see the diagram. So this is how a decision tree will look like for you. So once you build it, and I will tell you the skeleton also. So if you see, I hope this is visible. The figure is not increasing, the fonts are increasing. So if you see, there are a few questions that are getting asked, and based on that question, some are getting split into the left hand side, some are splitting to right hand side. We are still asking the question of yes or no. If it is a continuous variable, we put a threshold. If it is greater than, less than, so on and so forth, and get splitted. Yeah. And another thing, for if you want to use sklearn, then give me a minute. Yeah, sorry. I want to just find input. So of sklearn, there are same scikit-learn. We have a model called decision tree classifier there itself. You can also vary some of the features inside the decision tree classifier. There are many such options. I told you information gain, gene impurity is one of them. I think the formal names, if you search for them, is ID3 and CART. Probably there are bigger libraries which handle those particular things. But eventually, sklearn has something called a decision tree classifier. Okay, this one will help you do the classification. Going down. Yeah. So if I use sklearn also, it will also help me plot a graph. Like it will find the graph for you. What is yes or no. Based on that, it will plot a graph for me. It also, I am not sure if it is visible. It says how many samples are there in the beginning. There are 14 samples. After split, it became 7 and 7. After splitting 7 and 7 become 3 and 4. After 4, there are 3 samples on the right hand side and 1 sample on the left hand side. And based on the questions that we chose, this is the output. And there is also a very nice data set called iris data set. I will probably, yeah, 527 already. I wanted to show you this. So iris data set is one of the data sets that is already present in, let's say, scikit-learn library. It's a classification of, let's say, iris based on some color, petal length, and so on and so forth. So the decision tree has been created using the sklearn. What I wanted to show you is this on the right hand side. If you can take a look, I hope everybody can keep their eye on the decision boundary 2D projection. Yeah. If you see, this basically shows you the decision boundaries in a decision tree. Hmm. Here there are two features. There is one on the left hand side is petal width, and there is one on petal length. Yes. And if you see on the right top, there is Setosa, versicolor, and virginica. So these are the three classes that we have. And the colors inside are like the, let's say, the peach color, the yellow color, and the blue color. They basically represent the areas for each of the individual classes. Okay? The peach color is for the red one, the yellow for the yellow, the sky blue is for the dark blue. Yes. But I hope you are able to see that the decision tree creates, it's not exactly like a straight line, rather it can create multiple straight lines, right? So it can use like, for example, if the question was earlier, if you look at logistic regression, uh, the logic looked like this, and anything beyond x is equal to 0, or let's say x is equal to 1, all were ones, and everything x is equal to 0, everything was a 0. Yes. We never had a chance, for example, let's say if x is beyond -2, there are also some ones. We cannot do that with logistic regression, at least in the binary classification stage. But here we can do that, right? So here, for example, if you see petal length, I am not sure able to see the number, but this is like 5 and somewhere between 2.5. Beyond 5, it is something else. Beyond this, like between 2.5 and 5, there is something else. And beyond this 2.5, there is something else. So in decision tree, we can create multiple decision boundaries. The only problem here is it's still like lines. as in the thresholds are on the X, like whatever the feature values are. Yes. If we wanted a diagonal, yes, for example, let's say petal length beyond something below a line or greater than line, that is something not possible in distant tree. Yes, I hope that is getting transferred through. So because you understand why, right? Because the observations, we ask a question, observation split it in half based on the threshold. And if you look at the threshold, it just splits the data set into these two halves. We can have more thresholds, but we cannot have like a diagonal thing that depends on two values at the same time. Yes. The valid question is, so we can design, okay, can anybody think like how can we design a diagonal addition? Anybody wants to type? So I hope it is clear. So we choose one thing, then we decide if it is greater than, lesser than in threshold, or we ask which category it belongs. And eventually it just splits the data into this portion, that portion, and better based on the split, it takes addition. That's why we receive this straight lines. And is there a way to make it a diagonal? Yes, that's the question. Hopefully, that is a question I'm asking today. Maybe in the next class, beginning of the next class, you can point me out if it is taking time. Uh, Fine. Fine. So this is what I wanted to tell about decision tree. There are two more things. Sorry, I will take 2 more minutes. What is the like inductive bias of decision tree? Anybody can tell me? So what does the model assume in the decision tree? Okay. Okay. So maybe it's like already 5:32. So I leave these two questions with you. What can we design a decision tree that can have, let's say, a diagonal boundary? Yes, specifically diagonal in the sense of diagonal in a graph also. You can take a look at that. And the other thing is, what is the inductive bias of a decision tree, right? Like, what does the model assume? Doesn't matter what the data is, what does the model assume? Because linear regression assumes the data is linearly related. Logistic regression assumes that the data can be linearly separated. That means if I pick one threshold, left hand side will be 0, right hand side will be 1. Yes. Then the only thing remaining is the two questions, diagonal and what is the inductive bias of decision tree. Fine. Okay. With that, if there are any questions, you can ping on. Otherwise, we are done for today. Logistic regression and decision tree.
Uh, I'll just add
Yeah.
one sentence
Yeah.
that it's important that the students practice with these models that you are explaining now and
Yes.
learn how to sort of invoke them using scikit-learn, because these are some of the things that we will do when we get to the materials part, whether classification or property prediction. And even, of course, these will be useful for the project also.
Yes. And the logistic of submission of projects, I'm trying to figure out something. I will let you know in the next class on the Monday. Yes. Okay. Thanks all. We'll meet on Monday 4:30. Bye.